Hello, bonjour, Sabah el Khair, Podzdrav. Welcome to the third tutorial of Statistical Mechanics, Algorithms and Computations from the Physics Department of École normale supérieure. This week's subject is a model of random clothespins randomly positioned on a line between two poles or boundaries. This model is equivalent to one-dimensional hard spheres. This model allows us to move forward very far along three directions. First, it is a prime example for the Asakura-Ozawa depletion interaction, which is of great importance for macromolecules, polymers, blood cells, and many other systems. This is what we studied in the lecture using the halo picture. Second, the random clothespin model can be simulated very efficiently. We started out in the lecture with a naive algorithm. But Michael will show a providential method that allows us to simulate hundreds, thousands, and millions of clothespins on a line without rejection and without any effort. Third, this fantastic algorithm will show us the way to solve the model analytically. Alberto will show us how to compute the partition function, how to sum up the virial expansion, and how to prove that this system, in fact, does not have a phase transition. Then Vivien will investigate the relationship between pins on a line with walls or poles and pins with periodic boundary conditions on a ring. He will characterize the correlation in this system and show that they are short range and that this characterizes a liquid. In what we will do, you will see that the analytical results are strong and the algorithms that Michael will present are superb. But don't worry, the Python implementations will be about 5 to 15 lines long only.
In this week's lecture, Werner presented the random clothespin model, a model with hardcore interactions, just like the hard disks we discussed earlier. We consider n clothespins of width 2 sigma on a washing line that is a line segment between boundaries at x equal to 0 and x equal to L, as is shown here. The pins are placed one after the other, but if an overlap is generated, we take them all off the line and start anew. This is again our familiar tabula rasa principle, and once more it gives us a flat probability distribution. It samples n-pin configurations with a distribution pi of x0 to xn-1 equal to 1 if the configuration is legal and equal to 0 if the configuration is illegal. This is in agreement with the equiprobability principle. All legal configurations have the same energy, E equal to 0. Our pins are in one dimension what hard disks are in 2 dimensions and hard spheres are in 3 dimensions. A configuration is illegal if 2 pins overlap. This happens if their centers are less than 2 sigma away from each other. Likewise, pins are not allowed to overlap with the boundaries. This happens if their centers are away less than sigma from x equal to 0 or x equal to L. Here is how the program can be implemented in Python. Of course, this algorithm works and obeys the equiprobability principle as it should. But just like in the case of 2-dimensional hard disks, it has a very high rejection rate. Output of the program is shown here. Is this the best algorithm for this problem, or can we be a bit smarter? Of course we can. In fact, we are able to sample n-pin configurations without producing any illegal configuration on the way. This gives us a rejection rate of exactly 0. What you will see now is an example of a rejection-free algorithm, and it is way more sophisticated than all the algorithms we have presented so far in this course. But how can we possibly achieve a 0 rejection rate? This works because we already learned from our experience with hard disks that in the full configuration space of legal and illegal configurations, the regions of illegal configurations are like the holes in a Swiss cheese. For the clothespins problem, we can actually remove the holes from the cheese. To illustrate the idea, let us consider this example of 5 clothespins on a washing line. The first pin could not be placed within the halo of the left wall. Likewise, the second pin cannot be placed within a distance of 2 sigma from the first pin's center, and so on for the other pins. Finally, no pin can be placed within the halo of the right wall. We can therefore deflate the washing line by cutting out these blocked regions. If we focus on the pin centers and glue the remaining line back together, we obtain a shorter washing line of the length L minus 2n sigma. Let us call the pin centers on this shorter washing line y0, y1, y2, and so on. Then these y's are related to the original positions x0, x1, x2, and so on the longer washing line by xi equals yi plus 2i plus 1 times sigma. Since every legal configuration can be deflated in the same way and gives a washing line, a shorter washing line of the same length, we realize that the legal configurations distribute the pin centers not on the long washing line, but on a shorter washing line of L minus 2n sigma. This becomes even clearer if we invert this procedure. Any chosen 5 points on this shorter washing line, for example these 5 points here, can be inflated back to a configuration of 5 pins on a longer washing line of length L. Let us turn this into a Python program. Start by randomly choosing n points between 0 and L minus 2n sigma. Then sort them so that y0 is smaller than y1, smaller than y2, and so on. And then finally take care of the inflation in one step. In Python, this gives the following program. We first choose the y's randomly between 0 and L minus 2n sigma. Then we sort them. And this line here takes care of the inflation. That is, it relates the positions y0, y1, y2 to the positions x0, x1, x2, and so on. Notice that the program is called noReject in honor of its remarkable rejection rate of exactly 0. Finally, you can see here a comparison of outputs of the programs directPins.py and directPins.noReject.py for 10 pins at a density of 75%. Visibly, they are the same, but directPins.py generated more than 500,000 illegal and therefore useless configurations on the way, while every single configuration generated by directPins.noReject.py is legal. Before moving on, please take a moment or two to download, run and modify the 2 algorithms discussed in this section. On the Coursera website, there is the algorithm directPins.py, which mirrors last week's directDiskBox algorithm. There's also the algorithm that Alberto we'll discuss in a few moments. And this algorithm is really beautiful. It allows you to sample configurations with 1,000, 1,000,000 or 1,000,000,000 clothespins without any rejection. Unfortunately, it is very difficult to generalize this algorithm to 2 or even 3 dimensions, mainly because the crucial sorting step then becomes impossible.
Michael just presented a rejection-free direct sampling Monte Carlo algorithm for a many-body interacting system. This algorithm is rooted in the fact that we can actually compute the exact partition function of the system, namely the number of legal configurations given by the following integral, where pi, as usual, is 0 if there is an overlap and 1 if there is no overlap. In Michael's derivation, the sorting step played a crucial role. We can do the sorting step in the above integral and obtain the following result, where the theta function selects between the n factorial possible orderings of the pin centers, the sorted one with x0 smaller than x1, smaller than x2, and so on. We can now apply Michael's deflation step and change the x variable to the y variables. We obtain this integral, where there is no longer overlap condition, but only the ordering of the y variables imposed by the theta function. Remember, the theta function picks out one of the n factorial permutations of the integral. So we can remove both the theta function and the n factorial, compute the integral, and get the final result for the partition function. This is a beautiful formula, which allows you to compute the acceptance probability for the program directpin.py that was introduced in this week's lecture. The acceptance probability is the ratio of the volume of legal configuration to the volume of legal and illegal configurations. To test your understanding on this concept, please let me ask you a few questions. Question 1. Select from the following 3 possibilities the correct expression for the acceptance probability of directpin.py. The correct answer is option A, because in directpin.py the centers are generated between sigma and L minus sigma, and because the volume of legal configuration is L minus 2n sigma power n, the partition function that we have just computed. Question 2. Select from the following 3 possibilities an estimation of the average number of rejected configuration that should be generated before having a single legal configuration. The correct answer is option B, because the number of configurations that we have to wipe out before generating a single legal configuration is in average the inverse of the acceptance probability. Question 3. Compute this number for a density of eta equal 0.75 and 15 pins. Is this number 5 millions, 50 millions, or 500 million? As anticipated by Werner in the lecture, the correct answer is option C. The acceptance probability is 2 times 10 minus 9, which means 500 million rejected configurations. Now, let us recall the virial expansion introduced by Vivien in tutorial 2. For clothespin, we can actually compute exactly the derivative of log z with respect to the volume, or rather with respect to the length L of the system. and we obtain this exact expression that can be written in an even simpler way, 1 over 1 minus eta, where eta is the pin density. Note that this quantity can be expressed as an infinite virial expansion, 1 plus eta minus eta squared plus eta cube, and so on. This series converges for all densities smaller than 1. This means that there is no phase transition. However, we note the divergence at the point eta equal 1, a special point where we have long-range order. Knowing the partition function, we can actually compute exactly other quantities, like the distribution pi of x that shows the oscillatory behavior that you have seen in this figure. In fact, pi of x is the probability of having a pin center at x, which is also the probability, given the pin center at x, to put the other pins on its left and its right. Let's try to place k pins on the left. This is possible only if we have enough space. The number of possibilities of doing so is the partition function of k pins in the interval x minus sigma. In the same way, we have to put the n minus 1 minus k pins on the right. Putting these pieces together gives the following formula, where the combinatorial factor gives the number of choices of picking k left pins out of the bucket of the n minus 1 pins that remains once we have placed the first one at x. In Python, this gives the following program. If you have doubts on our calculation, you can compare these results with the results that I've just shown from the numerical simulation. The function pi of x increases steeply close to the poles. Our formula allows us to see that the distribution pi of x for x equal to sigma is a factor 1 over 1 minus eta larger than in the center. This becomes very large at high density, where the pins are strongly attracted by the wall. In a few moments, Vivian will show us that the attraction of the wall is not a simple boundary effect. The same attraction acts also between two closed pins. Before doing that, please take a moment, download, run, and modify the program we discussed in this section. On the Coursera website, you will find direct pin density.py. Its output should give you the same results as the numerical simulation performed with direct pins no-reject.py discussed by Michael.
Several times throughout the lectures and the tutorials, we are generating annoying situations by putting particles in a box rather than allowing for periodic boundary conditions. For instance, in the adults game on the heliport, we could have allowed a particle which exits from the system from the right to enter back the system from the left. Nevertheless, such strict but realistic rule of the wall has allowed us to learn about the metropolis algorithm. That is, how to treat rejections. The same objection can be made for our system of interest, the pins on a line. If the probability distribution pi of x is oscillatory close to the boundaries, this must be due to the poles. Now, it is true that the probability depends on the position because of the poles, because of the boundaries. This raises the following question. With periodic boundary conditions, this probability is uniform. So, does it mean that our discussion above was useless? Not at all, as we now discuss. By examining and comparing the two situations where the pins are put on a line to the situation where the pins are put on a circle, that is to say, with periodic boundary condition. Let us first write a program to simulate our periodic system. We start by putting a particle or a pin at position L minus sigma. Its right side provides a pole at position x equals 0 due to the periodic boundary conditions. This leaves us with n-1 pins that we have to put between 0 and L minus 2 sigma, where L minus 2 sigma is the left side of the pin we have put initially. All in all, this means that our system of n pins on a circle of length L is completely equivalent to a system of n-1 pins that we put on a line of L of length L minus 2 sigma. Besides, to ensure the invariance by translation, we shift the centers of the pins by the same number which is drawn uniformly between 0 and L. In Python, this gives the following program. Direct pins no reject periodic.py. By running this program, we observe that the distribution pi of x converges to a flat function as the number of samples increases from 1,000, 10,000 to 100,000. You notice a sharp difference compared to our previous boundary condition. The oscillations of the distribution close to the pole have vanished. But beware, this does not mean that there are no correlations in the system between the pins. To study such possible correlation, a good tool is provided by the pair correlation function pi of x and x prime, which represents the probability of having a pin at position x and another pin at a position x prime. This correlation function is a useful tool. For instance, it is trivially equal to a constant if there are no correlations in the system. Now, let us analyze the pair correlation function using the following program. Direct pins no reject periodic pair.py. Let us fix the density eta to 0.9 and increase the system size at fixed pin width to sigma equals 1. You observe that the pair correlation function quickly converges to its thermodynamic limit in the example displayed here for system size equal to 100, 500, 1000 and 2000. You notice that this pair correlation function presents oscillations in the same way as for the distribution for the system on a line. In fact, those two functions are the same because the pin which is at position x acts as a pole for the pin at position x prime. Indeed, remember now how we devised our simulation. We first put a pin at position L minus sigma. Using the same reasoning, you will convince yourself that the following formula holds. It relates the pair correlation function for a system of n pins on a circle of length L to the probability distribution pi for n minus 1 pins in a line of length L minus 2 sigma. Besides, Alberto explained to you previously that this function can be analytically determined. Hence, to summarize, we have constructed a system which is exactly solvable, in which you can compute in an analytical way the pair correlation function in one dimension and for a system where there are non-trivial interactions between pins. Let us now physically interpret the features of this correlation function. As you see here, the oscillations are embedded in a decaying envelope, and the correlation goes to a constant at large distances. To be more quantitative, let us plot this decay in a logarithmic scale. As you now observe, the linear behavior indicates that the correlation function decays exponentially as e to the power minus x divided by psi. Psi has a physical meaning. It represents the correlation length between the pins in the system. At pin density eta equals 0.8, its value is approximately 2. Increasing to a density 0.9, we observe the same behavior, now with psi equal 6, and a dramatic increase to psi equal 26 when eta is equal to 0.95. In fact, one can show that the correlation length psi diverges as the density eta goes to 1. Alberto has shown that the partition function of our system of pins in one dimension can be computed and is analytic for all densities, which means that there are no phase transitions. This is now supplemented by the fact that the pair correlation function, which can also be computed, decays exponentially on a length psi. This length psi, which is the length of the correlations between the pins, remains finite even if the system size goes to infinity. At distances larger than psi, the system is homogeneous. This is what defines a liquid state. Long-range positional order is possible in our system only at density equals 1, that is for L equals 2n sigma, that is for configurations where the pins are close packed. What we have shown concludes our study of this one-dimensional model, but in fact, what we have found, the exponential decay of correlation function and the absence of phase transition, is in fact generic in one-dimensional system with local interactions. Naturally, many subjects remains to be studied, especially if one wants to carry out the insights we have arrived to from dimension 1, realized in wires and tubes, to dimension 2, surfaces, interfaces, and even to dimension 3, bulk materials.
In this tutorial, we have gone quite far in our study of the random clothespin model, in other words, of one-dimensional hard spheres. We again obtained a beautiful relationship between the algorithms and the analytical solution. The providential direct sampling Monte Carlo algorithm showed us the way to the analytical solution of the model, the calculation of the partition function, of pair correlation functions, and of the density distribution. From a physical point of view, we saw that the system of random clothespin is a liquid. There are some correlations close to the position of one pin, but these correlations decay exponentially. On large length scales, the system is homogeneous. So again, in small distances, you have structure like in a crystal, but on large distances, it's homogeneous like in water. So this system is a liquid. This week and the previous week, we studied hard sphere models. And maybe you wondered why we never mentioned velocities or the temperature. This was possible, in fact, because the systems we studied are athermal. They are the same at all temperatures. Wait until next week, when we will discuss the Maxwell and Boltzmann distributions, and take up what was missing today and last week, the discussion of velocities, of temperature, and of finite interactions. Until then, have fun with the homework session 3 of Statistical Mechanics, Algorithms and Computations.